All right, this is a bit of an experiment. I have done long form videos before in which I show how to, say, upgrade a utility or how to debug a problem I'm having. But I've had some requests to give a video that shows the complete process end to end for creating something, say a utility or a library or an application. Now, I'm getting pretty close to the end of development for version 1 of C64 OS. In fact, this is my remaining list of things to do. So I've just finished the opener utility. I've got the open utility, the save utility, and the places utility. Open and save are going to share the majority of their code, but they'll be a little bit different. And then after that, I'm playing around with the idea of either upgrading gallery to use the toolkit, or perhaps introducing a new image viewer application before the release. So I therefore have to do the places utility. So I thought, well, maybe that's as good a place as any to make a video to show people how to make a utility. So let's start off with what places is. So we're going to load our startup script here, and then we'll hit F2 to boot into C64 OS. So I'll just explain this while it's booting up. So from the file manager, there's a Go menu, and you have the option of choosing 3 built-in locations, built-in places. Those are the system root directory, the applications directory. So here we are. So we have so the Go menu lets you go to the parent directory or the root directory of the current device. But it also has these sort of hot locations. So these 3 are built in. We can go to the system directory. That's where we are right now, actually. We can go to the applications directory. We can go to the utilities directory. Or we have these 4: documents, games, music, and pictures. These are also assigned function key shortcuts, although they're not labeled here because they're not triggered by the menu system, but you can push F1, F3, F5, F7, or you can push F2, F4, and F6, and those make sense based on the way the Commodore 64 function keys work. So these ones go to static locations, but these ones actually not quite. So the system directory is dynamically defined. These ones are static offsets from the defined system directory. But these ones are fully defined. So when we pick documents here, what it actually does is it loads. We can use the status bar to see where that is. So this is partition 1. This is OS docs. Okay, doesn't have to be in the system directory though. So let us go to, say, games. Okay, as it happens, this is also in the OS directory. Music. Okay, so here's a good example. I chose music, and it's taken me to device 8, partition 7 root directory. That's just the way I set up my partitions. If I click on my CMD hard drive here, I can see that partition 7 is audio. So, I set up music to go to audio. Similarly, I have this graphics partition 6. So if I say go pictures, probably, that's right, yeah. So I've configured it to go to 6. So what I wanted to do is I wanted to create probably under options, just how you can see here, like add favorites and open favorites. I wanted to have a thing that says places. And so basically it would just be a way to open a places utility And then that utility would allow you to customize where these guys go. So let's now go to the system directory using that Go menu. And then from there, we can go into settings. Okay. So you will see that we have this file, and this file, and this file. And there's one other, wherever it would be. Path file. There it is, docs. This file. So we have these 4 files, and they all start with, so docs.path.t, that's going to be documents. Games.path.t is games. Music.path.t is music. And pictures.path.t is pictures. So if we select just one of these files, and we say open that in text view, what we see is a serialized, this is a serialized C64 OS file reference in it. It's serialized so that it can be put into a string or so that it can be put into a sequential text file. Let us open now, say, game, no, not games. Let's say, yeah, games. We'll open games. Like that. So here we see this path, OS games. So what I wanted to do is create a utility such that you navigate to a path. So let's say we want games instead of, so games currently points to OS games, okay? But let's say what I really want to do is I want to point that at my games partition over here. Okay, so this is a list of games, completely different place. So what I want to be able to do is basically go to this place and say, oh, here are my games. Now what I'm going to do is say copy place, okay? Now once I've copied place, this place is on the clipboard. So we can pop open the clipboard to see that's the path to this place I just copied, okay? But now what I want to be able to do is say, go options, open places, and that'll pop open a utility listing the 4 configurable places, and then I can just paste the copied place into that line and hit save, and it'll write that place out to the appropriate file in settings. So that's how it's going to work. So the way that I do this, to start with, I mean, we start with the concept, right? We know basically what we want it to do. Next, what I usually do is I mock up, let's see if we can get this into focus. So I mock up my utilities and other application user interfaces on graph paper. Graph paper is truly my favorite. This is going to be a purely toolkit-based user interface. So basically what we'll have is one containing view that wraps everything. And then we've got a label, a label, a label, a label, and those will stretch all the way across to include this little F1, F3, F5, F7, just to let you know that those function keys trigger these options from the file manager. And then we have a TK input, 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 input. And of course, TK input automatically supports copy and paste. So we can literally, we can go to a directory, choose options, copy place, while this utility is open on the screen, in fact, and then we can simply drop the cursor into, say, the games field, hit clear, hit paste, and boom, we've got the serialized path in there. Then when we close the utility, it will simply save everything that's changed. So we want to kind of, or maybe it'll save everything, because I haven't quite done the code yet for did change. That's something I need to do. And then lastly, we just have this reload button. Now this is kind of, it's kind of a debate, you know, what's the best approach from a user interface standpoint. Should it be a save button there? You know, with a reload, should this be a save button and this be a reload button? And then maybe when you close, it's, well, what I prefer is you open the utility, you make a change, you close the utility, it saves. But if you come into the utility and you make a change and then you realize, oh crap, I don't want these changes, you can hit reload. That'll reload everything from disk. And if we were keeping track of what's changed, it would reset everything back to not changed. And then when you close, it doesn't have to save anything. Okay. So let's drop out of basic now. Or let's drop back to basic now. So we'll run our start script again and see what time it is. So let's start by going to OS settings. We'll do a list of star.path.t. Okay, so these were the files that we were just looking at in File Manager. And we can also look at them here, docs.path.t. Okay. Now here's another little, just before we really get going, I have a tool, so we can launch, we can load and run a tool called data check. Now the reason I use data check is to see, is there a carriage return at the end of this? Is there a null byte? You know, whatever. I just want to know what's in this file. So we'll go docs.path.t. Okay. So no carriage return. No null terminator, no carriage return. Okay? That's important. Okay. No carriage return, no null terminator. Let's run that on one of the others just to be sure. Pictures.path.t. Okay. Games.path.t. Okay. Okay. So we're pretty sure we know how these things are structured, right? Next, let's go to OS utilities. Now, here's my list of utilities. So I got my utilities in here, plus I have my source code for the utilities. So for example, you can see calculator.a is the source code for calculator, the actual executable. We've got today.a, and here we have the actual executable. We got about C64 OS.a, and we have about C64 OS. My typical convention, I mean, this isn't necessary, but my convention is that the source code files are all lowercase, and if it's an assembly file, if it's assembly code, it ends with a .a. And the actual executable should be in very human readable form. So, you know, file, info, it's got a space, it's got caps, there's no extension, you know? So because this is what's actually going to show up in menus and in title bars and so on. Now, the next question is, what do we want to base our utility on? So we need to do some file writing. We need to have a toolkit-based user interface. And we're using a custom class. That's the TK input class. So we need some code to load the TK input class. Now I could do this from scratch, but that's hard because you got to remember everything, right? So what I'd rather do is kind of start with a utility that contains already some of those elements. So, you know, I can look at my list of utilities here. I mean, I do everything on paper, right? But can look at my list of utilities. So these are my list of utilities, and these are features that they contain. I have this grid that indicates, you know, the little boxes are things I'd like to add in the future, and the X's are things that these utilities already have. You know. So let me just think about this for a second. Maybe file info would be a half decent one to be as our starter. Okay, so let's try that. So I'll hit F3 to open Turbo Macro Pro, and I will load in file info.a, and we'll just quickly review this to see what sorts of things it does. So it's got our TK input. That's handy, and it's got labels and buttons. That's good. It uses Toolkit, obviously, so that's good. This looks to me like it uses some custom keyboard handling. Now, do I want custom keyboard handling? Do I want custom keyboard handling? I don't think I'm going to need custom keyboard handling, but that's okay. We can remove that. So directory loading, I'm not going to need to load a directory. So we'll be able to strip out some things. I don't need to load directories. Got a list of views. It's got a draw context and a toolkit environment. It's got some custom config. I don't think we're going to need much custom config, except for the locations of where the utility is on the screen, but that's handled automatically. It's got some string labels, so that's really handy because we're going to use this, right? So we'll edit this. Right, then it has some code for loading in the custom class, so that'll be super handy. Okay, now the other thing that it does is it's got these shared libs. So it'll load in the directory library, the file lock library, the file copy library. But I don't think we're going to have to need any of those. I don't think we're going to need any of that. But here's the code for creating the toolkit environment, loading in the custom class, and linking it to its parent class, loading in the shared libs that we can strip away because we don't care about that. And then this is the code for setting up the user interface. So that's cool. We'll keep that. I'll just skip by that for now. We'll come back. We will come back to get into all the details. I'm really just previewing this for myself. We can skip this metadata. We can cut out that metadata stuff. Setting a first key view. Yeah, I don't think we're going to do that. I think we can strip that out. Okay. Some dirty code. This is our custom keyboard commands. Yes. So Command Z is not built into the TK input class. So for file info, I actually implemented TKZ manually. I don't think we're going to implement that personally. I think if you screw it up, you can hit the reload button, or you can always just pick a place again and copy it and paste it, and you're done, right? So I don't think we're going to support that. Message command for file open, I don't think we're going to support that, so we'll just strip that away. A lot of this stuff is removable. This is refreshing the directory. I mean, you know, it's easier to cut stuff away than it is to remember how to add it in the first place, right? Okay, so we don't care about any of this stuff. This is all just the... this is all just, you know, setting a file log, renaming a file, copying a file. Okay, so that's it for file info. And then we get down here to the linked library methods. And we get down here to some system calls. And the character map for the buffer. So this is the memory for this is the buffer into which the Toolkit UI draws itself. So normally I put that at the end of the utility code. So we just write our utility code and it gets loaded way up high in memory. And then wherever the utility code ends, the screen buffer that gets composited into the, like basically this is the panel buffer that gets composited onto the screen. It gets buffered into the end of memory. Okay, so I'd say that this one's pretty good. You know, it's pretty good. So let's just start terraforming it. Here we go. So we're going to rename this to places.a. Okay. And I think I need most of these, but if I don't need directory. And to be honest, I don't think I need IO or IOIEC. But I probably need most of these other ones, but we'll come back to those. So let's just review what's going on here. There's only one actual include with a static path that I use. So it's to OS headers modules.h. This not only brings in the ability for the utility to access kernel modules, modules is for kernel modules, but it also brings in these very standard include macros, and they just make life so much easier. So this inc.s is going to include OS s app.s. Okay, and so similarly for all these, this will bring in OS s colors.s. And those S files, I don't remember exactly now why I used the word S, but I use S files in the S folder, the S directory, for constants, macros, and so on. They're not exactly headers. The H is for headers, but the S is for things that are not headers, but you know, constants and macros and stuff. And we can review those if you want to know what's in those. But these are all the headers and all the S files. They're all included with the operating system, so you can review them at any time. If you want to see what's in app, we can go like this. So here's the thing: app.s is just the labels with no notes. That's what actually gets included by the assembler because it's much, much faster. But that file is generated by me from a more detailed version called app.t, which is basically the text version. So this has got comments, and it tells you what everything's for, and it's all spaced out, and it's got section breaks and so on. So if you want to, so you can use this kind of as documentation, and you just know that every label that's in here gets exported from this file into the same named file, but instead of .t, it's .s. Okay, and then that's kind of obscured by this macro, so you don't really notice that it's loading in the S one. So you could just look at the T one, but when you use this macro, it's actually the S file. This is the stripped down one that gets included. Yeah, so basically what we need here is like we've got a standard set of constants and macros and stuff that we're going to use. Then we've got the utility framework. This is just the offsets to standard routine jump table offsets for the utility framework. Then we have constants and macros that belong to these kernel modules: file, input, memory, screen, service, toolkit. Those are all kernel modules. Next, we have toolkit specific ones. So these macros, inc, tkh, that's to the toolkit headers directory, which is different. The toolkit headers and the toolkit macros and constants are separated out just so that they're more cleanly organized. So this one brings in the list of classes and some other constants. This brings in a list of sizes, just helps figure out how big the built-in ones are. Then we've got constants for each of these classes, and we've got headers for each of these same classes. Okay, sometimes you don't. So for instance, sometimes you don't need every one that's here doesn't necessarily have to be here. So input, there just is no header for input. So, utilities are always assembled to util base. Now you don't really need to care where that is. It happens to be E000. And the definition for where this is comes from the fact that we've included this app macro. So we can look at that. I mean, if you want to see that, it's right here, right? So this is where an application is assembled to. This is where a utility is assembled to. Okay, so that's, just in case you're curious. Now, immediately following, this is where the code starts, right? Is E000. Immediately following that, a utility must have a standard set of exports. This is a table. Now, for the absolute minimum, from the perspective of the kernel, you only need these. However, if your utility is going to make use of the utility framework, which it totally doesn't have to, but you'd be an insane lunatic to not use the utility framework. I mean, I wrote it because I'm lazy and I don't want to have to do all that stuff for every single utility. So if you want to use the utility framework, you have this extended exports. Okay, so we can go through these. Identity is, so these are pointers to things that are further down in the file. And the reason why we use offsets is because where these things get pointed to is kind of arbitrary, and you can rearrange them. It doesn't even matter. You can put other stuff between them, but this export table must come in this order, and it must come at the very beginning, and it points to the various things that the system needs to integrate the utility. So identity is right here. In fact, it is what identifies the utility. So the utility framework will use the identity to create the config file automatically. You can open the utility by name. So maybe in the future we'll write a utility that lets us type in a name and hit open in a text field, and all that would happen is whatever you type in the field, it would take the string you've typed in and it would literally pass that directly to the kernel's load util method or routine, and it would take what you've typed in and it would use it to open the utility. So it's also used to figure out, like, if you try to open a utility but a utility is already loaded in, it takes the one you're trying to load in and it compares it to the identity of the one that's already loaded in, and if they match, it just doesn't do anything. Next we have our init util and quit util. Those are called by the kernel. to tell the utility you've just been initialized. So it loads it in, and it loads in some other things, and then it calls Init Util once when the utility is first loaded in. And that allows you to configure your user interface, and load in your custom settings, and whatever you want to do. Quit Util gets called automatically just before this utility is going to get expunged from memory. Could be because the utility is going to be quit, and it's going to be and the whole section is going to be replaced by like graphics memory. Or it could be that the system is about to load in a new utility. So quit utility is there to clean everything up. You got to free your memory. Some types of classes need to be deleted because they do other things, like they load in shared libraries, and so you have to delete them explicitly in order to let them know that they need to deallocate their resources, and it's kind of recursive like that. And then finally, for the kernel's requirements, we have message command. So the application and the system at various times send messages to the utility, and they send them via the routine that's pointed at here. And if you don't want to support messages, you can actually just, you can make a shortcut. You can point this at like a routine that just sets the carry and returns, and that's like built in to the low level system. So for example, if I don't want to support messages, I could just go like this, set carry RTS, and that is defined in one of the files up above, and it literally goes to a low-level place in like workspace memory to a place that is guaranteed to be nothing but a set carry and an RTS. And the carry is used to tell the person who sent the message whether the message was actually acted upon, like whether the message is handled or not handled. So if we just drop this in here, we just basically reply to every message immediately, not handled, not handled, not handled. Put that back in. So next though, because we're definitely going to be using the utility framework, we're going to include this extended exports table. So this consists of a pointer to the screen layer. A screen layer is a structure, so here it is here, but we'll come to that in a second. Next is a pointer to the draw context structure. Now, so like let's say you're not using the utility framework. If you're not using the utility framework, it's like you could do things real crude. Like you could implement all the drawing manually. But if you are using the utility framework, it at a minimum requires a draw context. It does not, however, require a toolkit environment. So there's these things are all layered on top of each other, okay? So the kernel knows how to deal with screen layers. And that's all the kernel knows how to do. It knows about screen layers, and it knows how to send events to screen layers. But then at a slightly higher level, you have draw contexts. And a draw context can embed a screen layer. Is that right? We'll come to that in a second. So a draw context interacts with a screen layer, at least. And a draw context allows you to point at certain memory buffers, and then there are kernel calls that allow you to make relative draws, and they get slightly modified depending on the settings, and they get clipped, and they get wrapped, and they do other things inside that draw relative to that draw context. Then you have a layer above that, which is the toolkit environment. So when you have a toolkit environment, the toolkit environment embeds a draw context. And the toolkit then backends on the draw context. So each of these things are stacking. You got a screen layer, and then you have a draw context, and then you have a toolkit environment, and then you have toolkit classes, and they all stack like that. So we're going to use all those, all of those. Next, we have a pointer to where our configuration data is, and we have 1 byte that indicates how many bytes of config data there are. Okay, so let us rename this. This is obviously going to take a while because I'm explaining everything. So we'll rename this to be places, capital P, and no extension. Screen layer. So here's our screen layer. Now, screen layer consists of this structure. It is 4 words, 4 pointers, and a single byte. Now, if you want to know, well, how do I'm a developer and I don't know how any of this works. Where do I? Okay, no problem. This is technically, you can find this just in the settings files. I'm going to put this in the programmer's reference guide, but you can also just find it with the files that are already there. So if we go to our OS screen, I mean, it's a screen layer. You kind of have to know where these things are, but they're pretty logically laid out. So screen layers are in the screen. So we go screen.t. Okay, so here are all the constants for screen-related stuff, and we got lots of notes in here that you can read. And so here we are. Here we have a screen layer structure. So these are the redraw the screen vector, handle a mouse events vector, handle a key command events vector, handle a key printable, slightly different type of event, low-level event, vector. And lastly, we have an index. This is the index of the screen layer, the way it's the stacking layer of the windows or whatever, right? So the backmost screen is 0. Typically a utility is 1. Some other thing might be 2, and then 3 is typically the menu layer. Okay? Almost nothing uses that intermediate layer. It's normally 0, 1, and 3. But 2 is technically there because I thought, well, you know, maybe something advanced in the future will use another screen layer. So, again, you know, you could implement these all manually, and some utilities actually do implement this manually. But our utility is just a nice, clean, super easy. It's going to use all the resources it's at our disposal. It's going to use the utility framework. It's going to use toolkit classes. It's not going to do any custom drawing. It's not to do any custom keyboard or mouse event handling. It's just everything's going to be plain Jane. So we are going to drop in here utility framework draw, utility framework mouse handling, utility framework key command handling, utility framework key printable event handling, and we'll initialize this layer to 0, but it'll get overwritten. So you want to know where these come from? No problem. What are we on here? We're on line 61. So you can see that we've included util.frame. So let's check out that for a second. Util.frame. Okay, this buffer is only 16 characters, so I'll say util.f*t. Not found. Let's try that again. Util.*s. Okay, that's a little better. So here we have the extended exports table. This was that thing we already talked about up at the top, the extended exports. Here we have a jump table for the utility framework. And so when we call ufdraw, ufpmouse, ufkcommand, ufkprint, these are what we're actually calling. Okay? Okay. Jump back to line 61. Now, following these, we have state variables, right? These could just be anything. Identity and screen layer are pretty common, but these are custom, so we don't need any of these. So I'm going to set a start marker on this line. We're not going to load in a directory. We don't really care about that. So we'll set an end marker, and we'll take a block, kill that block. Okay. Now, next, this is kind of a cool thing that I have written. Yeah, you could use a label for every single view in your view hierarchy, but it's kind of unwieldy in my opinion. Like, it's a lot of labels, and it's hard to come up with names for all the labels. So what I have is kind of a simple data storage mechanism that I call a store. And a store is only for 2-byte pointers. So what you do is you have one label, and then after the label, you just have a series of word pointers. And then there are macros called store get and store set. And the only thing that they do is they get and set what's called a reg pointer. Okay, so a reg pointer in C64 OS parlance is a register-based pointer. And the standard reg pointer, whenever you see reg pointer, that's what this means, is X is the low byte, Y is the high byte. So this views label becomes the name of a store. I don't know if you can see my fingers. A store for basically an array of 2-byte pointers. So let's say, these were the fields in file info. So let's say you wanted to get the rename button. Well, that is index 3, right? So you could say store get views 3, and it will set a reg pointer that points at your rename button. And then from the reg pointer, you can do whatever you want. You can pass it to something. You can call the toolkits pointer this, and pointer this basically takes a reg pointer and configures the this pointer and the class pointer relative to whatever object is pointed at by the reg pointer. And then inversely, if you create, so let's say you want to create a new class, and you get a reference to the class pointer first somehow, which we'll see later. Get a reference to the class pointer, and then you'll call tk_new with the reg pointer to the class, and that'll create a new instance of that class, but it returns it as a reg pointer to the new instance. And so now that you have a pointer to the instance in a reg pointer, you can say store set views 5, say, and that will take that reg pointer and write it into this array at views 5. So it just makes things really easy, really easy. So what I'm going to do here is I'm going to think about all of the views that I need a reference to. So let's just take a look at this. So we got a bunch of views, okay? So in order to organize a bunch of these views, we need at least one root view, because the Toolkit environment always has one root view. So, it could be like, it could be that, let's say you wanted like this to have like a tabbed interface. It's like, okay, the TK tabs could actually be the root view, right? TK tabs descends from TK view. You need something that descends from TK view to be the root view. And why not? It would just be, you'd get tabs. Or like maybe you want the whole damn thing to just be a scroll area. It's like, okay, you can make a TK scroll view be the root view. But in this case, really the only thing we need is just something to contain a bunch. So a plain Jane TK view is going to be our root view. Now, we don't need to store the root view in this array because the Toolkit environment needs a pointer to the root view. So when we create the root view, we actually store the root view into the Toolkit environment. And therefore, we don't need to keep a separate reference here. Now, after that, we're going to create some labels, we're going to create some inputs, we're going to create a button. But the thing is that, honestly, like once I create the labels, I'm never going to touch those labels again. It's not like I need to update them or hide them or anything like that. I never need a reference to them. So I'm not going to store a reference to them. The only thing I'm going to do is I'm going to store a reference to the ones I actually need to get to. So 1, 2, 3, 4, 5. Here's now what I'm going to do. Here's just what I do. I draw a tiny little number. I draw a little 0, a little 1, a little 2, a little 3, and a little 4. Okay? So I draw a tiny little 0, 1, 2, 3, and 4 to remind me what my views index is for each of these guys. Okay? Now for labels like these, and also for this guy, usually what I do is I put a string index. So that's another kind of data storage which we'll look at. But I'll say that my string indexes are going to be 0, 1, 2, 3, and 4. Okay. So we can see I've put in this little 0 for this label, 1 for this label, 2 for this label, 3 for this label. And so 4 is for this label, and this 4 is for this button. 4 is to the button object, and this 4 is to the button object's string text. Okay? So now I can reference my document, and I can say, okay, well, I need five views. Okay? And we'll simply, we'll just label these. We'll go, this is our docs field. This is our games field. This is our music field. This is our pics field. And this is our reload button for OK. Okay. So next we've got a TK input delegates. You know what? I'm just going to get rid of that. So next we have our draw context. So recall, this is points at our draw context. And our draw context, again, you want to know where the draw context comes from? It comes from context draw. Okay? This is the draw. This is where you can read all about the draw context. Okay? So there you go. You can read all about the draw context. But what we need is, I'll just describe how it works. You have a pointer to the character map. You have a pointer to the color map, which on a Commodore 64 are two different blocks of memory. You have a current draw width, which is by default it's the full buffer width. So you have buffer width, which is the buffer width. The current draw context width, it always begins the same size as the buffer width, but the reason why these are different is because as the toolkit hierarchically draws, the toolkit manipulates the draw context by setting, these here are offsets, and there's a height, there's a width, a height, and offsets, plus there's a buffer width. So the buffer width never changes. But the width and the height and the offsets, they get adjusted by These are actually scroll offsets, I apologize. So these are origin offsets. These are scroll offsets. These are width and height of the drawable box. So as Toolkit is hierarchically drawing, it's manipulating the draw context, and it's also pushing this onto a stack, and then it's manipulating it, and then it's drawing relative to it, and then it might recurse and push that onto the stack, and then manipulate it again, and then draw relative to that, and then it'll pop the previous context off the stack, and then it might manipulate it again, and then eventually, when it pops back off the stack, you get back to what you've got here. So all that is to say that the buffer width it's the actual width of, the buffer width is like from here to here in memory, right? So the way that works is that, like, if your buffer width is, I don't know how wide this is, let's just say it's 30 characters or it's 28 characters. If you want to draw vertically, the draw context, if it's currently here but it wants to draw a character that's below here, it has to know how big the buffer width is. So it actually adds to its draw pointer the width of the buffer, and it ends up in the character that's immediately below where it was, right? So it uses the buffer width to determine how much to advance the pointers in order to get to some relative place on a line above or below. Okay, so char map and color map, where are those? They could be anywhere. You could, in your init method, in your util init routine, you could allocate some memory from like main heap memory, and then you could just take the pointer from the heap memory allocation and you could set it into this draw context. But that's not normally what I do, and you don't have to do that. You can instead, what are we on here? Line 69. So you can instead just put your draw buffers at the end of the code. So here's our char map and our call map, and we just need to put in here char map and call map, and they point to, boom, those two buffers. Now, what we need to do now is count up. We need to figure out how big this panel is here. So I'm going to do that really quickly to be grammatically correct. So we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So this is 24. And we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15, 24. Okay, so I just quickly count up, 24 wide, 15 high. Okay, so now we can plop these in. Okay, so we'll go width is 24. Buffer width is also going to be 24. Height is, what did I say, 15. Okay. Scroll offset's default to 0. Now, what we need to do is we need to know, well, how big is that, right? So use our calculator. We'll just go 24 times 15. So we get 360 bytes. Okay. Times 2. 350 bytes times 2, because we got a color map and a char map. So what I'm going to do, honestly, you don't really need these. This is kind of a holdover from the way I did it in the past, but I'm going to maintain it for now. But you don't really need to do this. So 1, 2, 3, 4, 5, 6 times 1, 2, 3, 4, because so basically what this is doing is defining a transparent top bar. That's like this transparent top bar. So initially it's set transparent, and then the utility framework is going to draw the bar into this. But I think the utility framework already sets these transparency bytes, so whatever. Next, what we're going to do is we're going to say, so 24, so we need to now advance this pointer. We need to leave room after this first bar for the char map, and then so that the color map and the char map sit 360 bytes apart. And so we got 360 bytes for char map, 360 bytes for color map. So we'll just go 24, that's the width, times 14, because this is 1, and then times 14, so we got 15 lines. So we'll just say 14 lines of A0, which is a different, that gets filled in by the utility framework. We'll just repeat that. And we don't even need to advance the pointer here, because it doesn't matter. There's nothing that follows this, so it'll just fill in the space. Actually, it's to your advantage to not set that pointer, because the extra, whatever, 300 bytes or 340 bytes don't have to be loaded in, right? If you did advance this pointer and put something after it, the assembly file would contain these extra bytes that you don't need. So this is going to be 14 lines of the panel's color. All right, let's pop back up to line 69. Okay, so next we got our toolkit environment. Again, TKN was pointed to by this guy here. So toolkit environment. Okay, so toolkit environment, again, you can look up where that is by going to toolkit.t. Okay, so here's your toolkit environment. Okay, there are all the flags for toolkit environment, plus a bunch of other crap which you can read about. But I'll just tell you how it works. So the first pointer is to the draw context. Okay, so this draw context is pointed to by the toolkit environment. Next we have a memory pool. So this is, the toolkit requires a memory pool such that when you go tk new to create a new object, it allocates from some available block of memory necessary for the size of this object, but it allocates it out of a memory pool. So we're kind of deep at the weeds here, but C64 OS divides memory into several kind of types. There's like reserved memory, so there's like kernel memory, which it never serves kernel memory. There's high memory, which is where like utilities and graphics data gets written into, which it never serves out of. Then there's like workspace memory, which is for the operating system and the processor, which is way down low in memory. And then in the middle you have the heap, and the heap is not just one continuous enormous heap, but the heap gets divided into what's called memory pools. So when you allocate a contiguous range of pages. So if you want to have a memory pool that's like 10 pages, you say page alloc 10, and it looks in the heap memory for a range of 10 pages that are contiguous, and it initializes them as a memory pool, and it returns you the first page, the lowest page of the whole pool. And then you write that page byte into this location. And then what you do is later on down the road, before you make mallocs, the memory pool, the low-level memory pool has to be set. And then when you call malloc, your mallocs aren't just simply coming out of like anywhere. They're coming out of only that defined memory pool. And so that allows like the system can create a memory pool, and the application can create a memory pool, and the utility can create a memory pool, and maybe another memory pool is owned by like a terminate and stay resident style program, or like a driver might create a memory pool. And then within the memory pool, the utility might be making individual allocations with malloc to its own memory pool, and then like the driver library might be creating not the driver library, but the directory library might be creating like directory entries into its own memory pool, and so on, right? Okay. So we got the draw context, the memory pool. This is a special flags byte that indicates a variety of sort of conditions of the environment, like whether the environment is dirty and needs to be updated, whether the environment is currently blurred or in focus, and other statuses about the environment. Screen layer, this is technically, it gets copied from here, but there are reasons why the toolkit needs to know what screen layer it's on. The root view, the toolkit needs, so whenever the toolkit propagates events, it needs to propagate the events starting, like if you click, it needs to propagate the click first to the root view. So the toolkit needs to know where the root view is. This is also why our views store doesn't have to keep track of the root view, because there it is. These guys, you don't have to, these are all just zeros. They're just placeholders for the toolkit's sort of working memory. But for example, like, what is the first key view? So for example, if you push a key, if you click, the click gets routed to the root view first, and then the root view figures out which view you actually clicked on. But if you hit a key, it's like, well, where does the key go? It actually gets sent first to the first key view. And then if the first key view doesn't handle it, it allows it to bubble up to higher views. First mouse view, that's used for like, so if you mouse down on a scroll bar's nub, the scroll bar's nub gets assigned as the first mouse view. And then as you move your mouse away and you move it up and down, the mouse move events actually continue to get routed back to the first mouse view, so that the scroll view is actually scrolling up and down. The scroll bar is moving up and down because you clicked initially on it, even though the pointer is way over here. And if you test that out on a modern operating system, that actually is how it works. Click mouse view helps with double clicks. You don't really need to care about that. Position X and Y, this actually is overlapped. So the TK environment basically has to come, you don't have to, but it's very handy, if it comes immediately before your config variables. And then the first two configure variables can be the position X and the position Y. Okay, so the toolkit needs to know the origin on the screen of where the environment begins, plus compositing the panel onto the screen. The kernel composites the panel onto the screen, and it uses its position X and Y. And when you drag the title bar, that's the utility framework that's moving it. But not only is it moving it, but it's also updating these numbers. And because the utility framework is updating these numbers, and these numbers are shared by the toolkit environment, they just cohese, right? I don't think we need this config variable. So we got two config variables. So we want to come back up here and adjust this guy to 2. Let's search for config size just to see if we actually need it. Okay. Yeah. So this is related to loading directories. And this is also loading directories. And that's loading directories. That's loading directories. That's loading directories. Okay, so basically the reason why I needed that for file info was because I use it for loading directories. But we ain't loading directories in this utility, and so we can actually get rid of this and just make this simpler. We'll just say that's 2. Okay, we'll leave a comment that it's the config size. Okay. Okay, so now we get into content. I basically divide my utilities into sort of sections. We have basically our includes, our kernel exports, our extended exports, our state. State's a little different than content. So state is basically everything you see here. Then we have config. Then we have content. Content is strings and stuff. So this is another kind of store, just like that views, store get, store set. This is a string storing mechanism. So what you do is you set one label, getStir, and then you have a macro. Right? Stir AXGet. And then you have a series of null terminated strings. And you can then call, you can put the index of the string you want into the accumulator, and you can jump to getStir, and this macro will look up the pointer to the string that you want based on the accumulator value you passed in. And it will return to you a pointer to the string. So there's 2 macros. One macro is get stir xy get, which will get you basically a reg pointer to the string. Or this is ax get. So it's a slightly different type of register pointer. This is a little bit more the way the kernel ROM defines pointers. And for some very technical reasons, like a couple of things in the toolkit prefer an AX pointer. I know it sucks, but there are so few registers on the 6502 that it's hard to not have a few little oddities like that. So what I often do is include a little routine AX to XY. And this will just convert. So, usually I'll use the macro here for the kind of pointer I need most of the time. And if I need like one of these, like maybe I'll need rename to be in XY, I can just keep it in this store, and I just use this little routine to just boop, boop, and swap the AX pointer to the XY pointer. So let's just get rid of all these. All right, so now we got our strings, right? So the title places, that comes from the identity, and this bar is drawn by the utility framework. This label, though, I'm just going to make it one label that includes these spaces all the way over to that F1. So if our total width is 24, our string length is going to be 22. So we're going to go like null, and then we'll go documents. What's that? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. This one should be text. Okay, I'm going to make that a capital F. So let's just count these again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Did I fuck that up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. I did fuck that up. Here's what we're going to do. We're going to go 1, 2. So we're going to go 1. That's 22. And then we'll go 1, 2. And then we'll remove that. Okay. So this will be string number 0. Put that here. 0. And we'll call this one games. And this will be string 1. This will be F3. Now, Turbo Macro Pro, text means that you simply have a series of bytes that are between quotes, and that's it. Everything between the quotes, that's how many bytes you've got. Null is identical to text, except that it adds a 0 byte at the end of your string. So following whatever's in the quotes, you get an extra null. And this get stir, or this macro, stir xy get, it delineates the strings by searching for nulls. So the strings using this in this store have to be null terminated. Okay, so this is pretty straightforward. I'm just gonna make a copy of this, like so. I'll say this is 5 and this is 7. Okay. And games will become music. And this one will become pictures. This is 2 and 3. Okay. And lastly, we just need reload. 4. Okay. Now, so these are going to be assigned to labels. So we got 4 labels, and the labels, the title of the label needs to be passed as an AX pointer. So 4 AX pointers. Reload, however, is going to be the title of a button, and the title of a button takes an XY pointer. So, you know, it's only 1 out of 5, and I don't want to repeat this macro because it's a lot of, it's like, you know, there's like a bunch of code. This macro turns into a chunk of code. So it's actually much shorter to just include this. And then we can use this macro to pull this, to pull an AX pointer to this. Then we can call this once to convert it to an XY pointer, and we're done, right? Next, we need to the TK input class is not built in because it's a lot of code and a lot of things don't need it. So I don't want it to be part of the kernel, or I don't want it to be permanently memory resident. So TK input is a reloadable class. So basically what we do is we have a string that says like, you know, the TK path. This is a relative path from the system directory. This is the name of the relocatable class that we want to load in, and then we have a pointer which will be to where in memory the class definition actually is. Okay. And so pointer, you know, I don't know if we'll need this, but if we do, it's just kind of a pointer to some random 0 page that's shared by everything. FB, FC, they're just empty, nothing uses them. Everything uses them, but they're very, very temporary. So next we have so we got our quit util here. So we basically, this is like, what do we need to clean up when we are quitting our utility? Well, we don't need to worry about directories, but we are going to need to deallocate our toolkit's memory pool. And we are going to need to free our customly loaded class, but we don't need any shared libs. So I'm just going to remove all this shared lib stuff. Okay. And the last thing that, so in our quit util, we do the things we care about. So we're going to free our toolkit memory pool. We're going to free our custom class. And then we're going to jump into the utility framework's quit method, which will do its own kind of cleanup, such as popping the screen layer and saving the config data and stuff like that. Okay. Now, how big of a memory pool do we need? All right, here's where things get a little bit manual. And you might think that this is a pain in the ass, but I don't know of a better solution for this. So, as I said before, we need a memory pool out of which these things are going to get instantiated. But I want the memory pool to be as small as possible. I mean, if I wanted to just ask for 10 pages and just use 10 pages, it's like, that's cool, I could do that. But what I really want is to just use the minimum amount of space possible just to instantiate this relatively static user interface. I mean, nothing's being dynamically created or dynamically removed. It's just, I know exactly what's here, right? So what I'm going to do is I'm going to draw myself a little hierarchy. So I'll say the root view is a TK view. And then inside the TK view, I'm going to have a TK label and a TK input. And then all of that is going to be times 4. And then I have a TK button. Okay, so this is a remarkably simple. Let's see if we can get some focus on that. It's a remarkably simple hierarchy, right? We have a view, and then nested inside the view, we have a label and an input, and of course that's times 4 because we got 4 of those, and then we have a button down here in the corner, and so that's it, right? So next, what I do, and what you could do if you use the programmer's reference guide, is we look up the size of these classes. So what we see is that, we have a table here. So these are the built-in classes and a bunch of data about them that I use for assembling them. And these are the relocatable classes. And this is basically like how big the class file is. So for example, our TK input descends from TK control, and it's 6 pages. That's the class definition. But the object size is 60. So it's 6 bytes bigger than what it descends from. So it descends from TK control, and TK control is built in. So TK control is up here. So TK control is 54. So TK input is 6 bytes bigger than TK control, and thus it is 60 bytes. Okay? So that's basically what I do, is I use this table and I simply say, okay, a view is 39 bytes. So we're a little 39. A label is 44. Okay. An input is 60. And a button is 62. Okay. But these are times 4, recall. Okay. So now what I do is I just use my calculator, add these up. So we'll go 44 plus 60, That's a label and an input times 4. Okay, that's 416 plus 39 for the view plus 62, and we get 517. Okay, so 517 plus, there's one other thing you need to take into consideration. Every allocation has a Malloc header, which is 3 bytes. So we have instantiated 1, 2, times 4. So a label and an input is 2 times 4 is 8, plus a root view is 9, plus a button is 10. So we basically need plus 3 times 10. 3 times 10. For a total of a minimum of 547. Okay, so that overflows 2 pages. 2 pages would be 512. So we need at least 3 pages, and then we've got some extra room to play around with. We can do whatever we want. And as it happens, look at this. We're already instantiating 3 pages because file info needed 3 pages. Yeah, 3 pages, pretty standard for a little control like that, right? For a little panel like that with some labels and buttons. So 3 pages, perfect. That's all we need to do for the quit util. Now for init util, this is much more complicated. So the very first thing that init util has to do is it has to do something called initialize the externs. So every application and every utility and every driver and every library for that matter, if they want to dynamically link to the kernel, which is highly recommended, okay, highly recommended, because if I change the kernel in version 2, which is likely, you don't want old drivers to break. So they need to dynamically link to the kernel. So to do that, excuse me, we'll just jump down here to our extern label. And here I have some linked library methods, but we got rid of those, so I'll get rid of our linked library methods. So now we have this thing called extern, okay? And extern, this is the list of the kernel modules and kernel calls in those modules that we need to bind to. Now, I'm going to clean this up, okay? Just going to clean this up real quick, just to make this cleaner for you. I can tell you right now, we don't need timers, so I'm going to get rid of that. Okay. And I don't think we need alert. We do need load relock. We don't need lib, so we'll get rid of that. Page lock and free we're going to need. To stir, I don't think we're going to need. I don't think we're going to need read k command, but we're going to need a couple of these. We're going to need fopen. I don't know if we're going to need finit. We're going to need fclose. We're going to need fread and fwrite. Okay. We're gonna need, I'm gonna change these to page free, page alloc, mark redraw. Yeah, I think we're gonna need that. Mark redraw. Get a system file ref. Yeah, we probably need that. Load relock we're gonna need for loading the custom class. And we're gonna need these. Set tk env, class pointer, pointer to this, tk new, get method, pen 2. Okay, and the so this is basically a kernel linking table. So the way that it works is you use inch and the name of a kernel module, and you get the header for that module. And if you don't need the module or any of its calls, you don't do this. So we need to be able to call fopen, fread, fwrite, and fclose. They all come from the file kernel module. So we go inch file, and then we write these syscall from the lfile module, and the same name here, but with an underscore. This builds a table that of jumps. It's a jump table, but the pointers when at time of assemble are not pointers to actual memory. They're pointers to something, but they're not pointers to actual memory. And so this is basically the list of the things we're going to need, but we'll come back to describe why we need these. And when you go to Init Util, the very first thing it does is it grabs a pointer to the externs table, and it calls JSR init extern. JSR init extern is defined in our app. It's the very next thing. We got our app base, our util base, and then we have this thing called init extern because it's used by freaking everything. It's very low level in memory. It's considered to be a component. So the booter installs certain components. This is one of those. It's a little chunk of code that's it's like essential, right? I mean, it can't be part of the kernel because it's designed to let things link to the kernel. And so it has to be something that's in a static place in memory, but that applications know about. And then it knows how to rewrite that table to point to the correct places in memory for where the kernel calls are. Okay? So unlike in our quit util, what we did was we freed up some things and then we called the utility framework's quit method, quit jump table entry. For initializing though, as soon as we've initialized the kernel jump table, we're going to call the utility framework's init routine right away. Now, what that's going to do is a whole pile of shit. It's going to prepare the screen buffer. It's going to push the screen layer onto the stack of screen layers. It's going to load in the settings from the correct file that was saved from the last time that we opened and closed this utility. It's going to initialize the colors of things on the panel based on the theme. I mean, it just does a bunch of cool stuff like that, right? And it has settings that we can set. So do we want it to set the title? Absolutely, we want it to set the title. Do we want it to clear the buffer? Absolutely, we want it to clear the buffer. Do we want it to have a global conf file? No, we don't need a global conf file. So if we don't have a global conf file, this utility's config data will be written into each application bundle where this utility is opened. Okay? That means that every application above which this utility gets opened, this utility can be saved in a different place on the screen depending on the application that it's opened above. Next, we are going to create our memory pool for the Toolkit environment. So here, page alloc, that's one of the kernel calls. We want it to be 3 pages big, and we want to mark the type of allocation as being owned by a utility. It's going to return the address of the 3 pages in Y. And by the way, if it can't allocate this, it's going to throw an exception. And so we take the memory pool start page and we stash it into the toolkit's memory pool structure. The toolkit environment structure at memory pool. Okay, so now our toolkit has a memory pool. Next, we need to load in our custom toolkit class. Now, if you were building your user interface out of, here's another interface, right? Here's another interface for a different utility. It's got a scroll view, and it's got some buttons, and it's like, well, all of these are built in. So if you want to build if you want to build an interface out of toolkit classes that are already built in, well, you don't have to do this. But the TK input class, it's too big. It's got too much. It's 6 pages. I swear it's 6 pages. I can't sacrifice 6 pages of 256 pages. 6 pages of 256 pages. Let's figure out how much that is. We'll go like 6 divided by 256. It's 2%. It's more than 2%. I can't sacrifice more than 2% of the entire computer's memory for some class that might not ever be used by the application that's running, right? I mean, it's not acceptable. Okay. But for this utility, we need it, right? Okay, so we are going to allocate another 6 pages. So this is technically a different allocation, right? So we're going to get 2 memory pools. We got a 3-page memory pool that we shove into the toolkit environment. So the toolkit environment is only going to use its three pages for instantiating all the widgets. Meanwhile, we're going to ask the kernel, hey, you know what? Give me another memory pool that's 6 pages big. And I'm going to use those 6 pages to relocate a chunk of code into those 6 pages. Okay? So it's going to be allocated as a utility, owned by the utility, and it's 6 pages big. And immediately after we call page alloc, the first page is in the Y register, and then we're going to call get a system file ref, but we're passing Y straight from memalloc into get system file ref. So what this get system file ref is going to do is it's going to configure the first page of the 6 as a C64 OS file reference that is configured to point to the device number, the partition, the path of where the system directory is. Okay? And when it returns, it's going to have a pointer to the start. So what came out of page alloc as Y goes into get sfref as Y, but it comes out of get sfref in X. The reason is because Y comes out of get sfref as the final byte of the path And I did that very specifically because you can use getSFRef as sort of the basic, configure me a file reference to the system folder. But I get Y and it's pointed right to the end. And so if I want to append to that path, Y is perfectly configured to continue on appending. So we take X and we set it into pointer, which was defined above, just a free 0-page pointer. Next we zero out X and we write the pointer's low byte as being 0 because this fref is page aligned to the start of this block that we just allocated. Okay. But now what we have is X is 0 and Y pointer points to the start of the file reference. X is 0 and Y is the end of the path. So very conveniently, we can then call this stir-add macro, pass it the pointer, and pass it a pointer to a string. Okay, so this is a 0-page pointer, and this is a string. The X is the index into this string, which is 0 because we want it to be the start of this string. But the Y is the index into the pointer, which is a pointer to file reference, which is a pointer to the end of the path component. And so boom, stir-add will simply add tk-path to the end of the path, which is configured as the system folder. Okay? Now, if you want to know, let's say you say, well, that's all well and fine, Greg. You created all this stuff. But how the hell do I know how PageAlloc works? I'll tell you. What you do is you reference the docs. So we go to OS headers. This is going to come from memory, right? Because it's a memory page allocking and mallocking and stuff comes from the memory kernel module. So we look that up and we can see all of the kernel calls here and what they take and what they return and what they do. So here's malloc, here's page free, so here's page alloc. So A is the allocation type. X is the number of pages to allocate. Those are the ingoing variables. So before you call this, you set A to be the allocation type, you set X to be the number of pages you want to allocate. And when it returns Y is the first allocated page address. And I was wrong. This routine does not generate an exception. It sets the carry if it failed to allocate the memory. Okay. Now let's say we want to say, well, what about getSFRef? Okay, that's a service. So we'll look that up in service. Okay. getSFRef. getSFRef takes in Y, and you'll recall that Y was what PageAlloc returned. It takes the allocated page into which to initialize the system fref. Or if you pass Y as 0, getSFRef will automatically allocate one page, but it'll be map system. It'll be owned by the system, not by the utility. And it will configure it as a system fref. And Y gets returned as the end of the path component. And X gets returned as the page of the new system fref. So if you pass Y in as 0, you need X because you're getting X back and you don't know where it got allocated, right? Because you weren't the one that allocated it. You said, you allocate the thing for me. And then it returns X. Now you know what it is. It also allocates fref pointer, but let's not worry about that for now. Okay, so that's kind of how you can figure out what these things actually do. Okay, so next what we want to do is we want to use a stirrad, but we want to use it to set the file name component of the file reference that we've just created. So just as before, pointer is the structure, the 0-page pointer to the structure. X, we reset X to be 0 because we want it to be the start of this string, the TK input name. And this time we set Y to be the index into the file ref structure for the file name component, right? So we say, okay, well, we want to set the file name and we want to get it starting from 0 of this name, and that copies the name into the file ref, okay? Next, this is a bit tricky. I must admit, this is tricky. So the utilities code is being run from behind the kernel ROM. And what that means is that there are some kernel calls that you can't make while you're executing from behind the kernel ROM. So this is kind of a Commodore 64 difficulty, but there is a provision to allow you to make a redirected call. So what we do is we want to call load relock, but load relock, it's like we're loading something from disk. It's got to come from the kernel. And so what we need to do is we need to patch the kernel in over top of our code. Do the load, do the relocated load. And then we need to patch the kernel back. We need to patch the kernel back out and have it return back to our code, which is under the kernel. So what we do is we read the pointer to the load relock kernel call from our own jump table that we established below, and we set it into the redirect vector. Okay, so we basically just say, okay, we need to make a call, but the call's in the kernel, and it's behind. It's behind where we are. It's like, who the hell knows? Maybe the load relock code would be like right here, except that it's not here. It's like it's in a ROM, right? So we grab a pointer to here in the ROM, we set it into a redirect vector. Okay? And then what we do is we jump to redirect. So we jump to here way down in memory. And that patches the kernel in, and then it jumps through the redirect vector into the kernel. And when the kernel returns, it goes back to the redirect vector, which patches the kernel out, and then it returns, and it returns back to the code that's running under the kernel. Okay? So it's a little bit complicated. It's not a complication that you have to worry about when you're writing an application, but it is a complication you need to worry about when you're running code from behind the kernel ROM. Now, some people have said, what do you have the kernel ROM for? Using the kernel ROM is so convenient. It's so convenient. But I'm not going to get into that right now. We simply set up our load relock into the redirect vector. Now what we need to do is we're going to load in a custom class. But in order to load in this custom class, we need to link it to its to the class from which it inherits or it descends. But the problem is that class is part of the kernel. And we don't know where that class is because it could move, right? As these classes change size and as the kernel changes size, it's like where that class is going to move. So we have a kernel call called class pointer, which is in our kernel. So we have that init externs table, which dynamically links to the kernel. So one of our calls is class pointer. So that's dynamically linked to the kernel. Then what we do is we say, I want the TK control class, and we ask the kernel, hey, where's the TK control class? And it returns a reg pointer to where that class definition is. Then what we do is we take that class pointer and we stick it into the actual class variable, okay, which is loaded way down low in memory, 0 page, I think. Next, what we do is we read in the address from the pointer. So we're reading in the address now that's 6 pages big, but that has been initialized to the system path, and then it's had the TK path added to it, and it's had the TK input R file name added to it. So you got this file reference. It's 6 pages, but the first page of it is configured to point at the file that we want to relocate and load. And then we take the parent class, we stick it into class, and we call redirect. And so what happens is that redirect goes through the redirection. It does a load relock. It uses the file reference to find the file, tkinput.r. It loads that 6 pages into memory. It actually overwrites that first page that was configured as a file reference, plus it fills up the following 5 pages with all the code. Then it relocates it. Then it calls its link method. And inside the class, the link method is used to, one of the things that it might do is initialize its own kernel link table, because the class may need to make kernel calls. So the class gets relocated, but then the class also has its own kernel lookup table. Now, you don't have to care about what's going on inside the class unless you're writing a class, but the class uses its link call to initialize its own reference to the kernel calls it needs. Plus, it initializes its own jump table to point to the class that is the thing that it inherits from, which it has gotten from class. And so basically the class links itself to the kernel, and it links itself to its own parent class, which doesn't have to be a built-in class, by the way. It could be another dynamic class that you've loaded in. So you could load in a dynamic class, and then you could take the pointer to that, stick it in class, load in another dynamic class, and now, this one links to this one, and this one links to one that's built in. But the final thing that it does is it takes a pointer to itself, its own class definition, the class definition you're actually loading in. So you pass in the one it's inheriting from in class, it uses that to link itself to that, and then it takes itself and puts it into class and returns it in class. And so what you get out of this is a pointer to a freshly relocated class ready to use. And what we do is we use this macro to copy that class pointer to this variable, which is up above in our content variables, TK input class. So we can now use it. Okay, next we got shared libs, but we're going to skip all this because we're not using any shared libraries. So now what we're going to do is we're ready to begin instantiating our user interface. So what have we done? It's like we've initialized we've linked ourselves to the kernel. We've initialized the utility using the utility framework, which kind of prepares the layer and puts the title bar and puts the layer on the screen and sets the themed colors. We have allocated some memory for a toolkit memory pool. We've allocated some memory for a custom class. We've configured a file reference to the custom class. We've loaded it in and linked it. Now we're basically ready to start creating the user interface. So we grab a reference to tkenv, our toolkit environment, and we call setToolkitEnvironment. That prepares the toolkit kernel module to be able to work with this environment. So now it's got a reference to the draw context, and it's got a reference to the memory pool to allocate it, and it's got a reference to like what screen layer it's on. It has all this sort of stuff, right? So we're going to so now we're in the process of creating and initializing and configuring and linking together our user interface classes. So we're going to make a root view. So same as before for when we found the TK control class pointer, you go, we want a view. That's a built-in class. So we go loadx with TK view, and we say, hey kernel, give me a pointer to the TK view class. It returns a pointer to that, and we can immediately call TK new, which is also a kernel call, and that uses the toolkit environment's memory pool to instantiate a new instance of TK view and creates that allocation dynamically using Malloc in the pool. So we don't need, like way down in our kernel table, we don't need to call Malloc. But Malloc's being used. It's just being used by TK new, right? It's like we're not actually calling Malloc. We don't even care how big a TK view is at this point. But internally, TK new knows, it looks up how big a TK view is and initializes that amount of memory, or allocates that amount of memory with Malloc from the mempool. It returns to us a reg pointer. This is the root view. So all we want to do is stick that pointer into the toolkit environment's root view property. Okay? So from now on, the toolkit environment's going to have a pointer to the root view, so it can route, it can route the various messages it needs to. Now, newing is not the same as initializing. Newing literally just allocates the memory and gets you a pointer to it, and that's it. But the memory is just like random. There could be a bunch of crap in there, right? So next we need to initialize. But what TK-new has at least done under the hood for us is that it has set the this pointer, and it has set the class pointer. So class and this. So class now points at the TK view class, and this points at the instance that's been allocated. So we say, okay, well, we need the initialization method. So we go init get method. So get method's a kernel call. And what that does is it gets a pointer to the method and puts it into a special vector. Between here and here, you set up the parameters that you want to pass to the init method. But in this instance, there are no methods to pass to TKViews init. So we call sysjump, and that calls the method that we've just gotten. And it calls that method on the context of this. This is what makes it object-oriented. It calls it on the context of this. And then this is using a reference to the class by a class pointer to get, get method actually is using, get method is using the class pointer to look up the class method. Okay? Okay, so after we've initialized it, view has all of its properties, like just a shit ton of, pardon my language, a crap ton of internal parameters are initialized. Anchoring properties and sizing properties and masks and like, whatever, and scroll offsets and a whole bunch of stuff. And so we need to override some of the basic properties. So it's going to have its anchoring. It's going to have its anchoring. I'm almost out of battery life, so we're going to have to, in a couple of minutes, we're going to end this video, and I'll make a part 2. So we're, by default, the view would be top, left, bottom, right, all of 0. And because it's the root view, it would be relative, like 0 would be the top of this, and 0 would be the side, and 0 would be this side, and 0 would be this side. But what we want to do is we really want the view to start here. So we're going to pull it down 1, 2, and we want it to start here. So we're going to pull it in 1. We want to start here. So we're going to pull it in 1. And from the bottom, I like having the view. I like having the button hang out on the bottom. So we're going to leave that as 0. And its anchoring is naturally, its anchoring by default is top, bottom, left, right. So we're going to use these macros to say, set this offset top 2. Set this offset left 1. And these are 8-bit properties we're setting here. And then we're going to say set this offset right 1. And then boonk, that's going to pull in that root view. And that's all we need to do for the root view. After that, we can move on to the next view. But I'm going to leave that for the next video because I'm running out of battery life and it's been 2 hours. So thanks for watching. We'll call this part 1.